Have you ever wondered how your eye keeps its perfect spherical shape? Well, it's definitely not just an empty ball. Welcome to this explainer. Today, we're diving into the incredibly dynamic system of intraocular fluids. We're talking about the fluids that are actively produced and meticulously regulated every single second of the day just to maintain your eye's internal pressure. Let's get right into it.
Here is our roadmap for today. We're going to compare the eye's two main fluids, map out the anterior and posterior chambers, hit some high-yield data on the aqueous humor, trace its drainage pathways, and finally, tie it all together with intraocular pressure and glaucoma risk.
Section 1. The eye's two fluids, a tale of two humors.
So, when we actually look inside the eye, we find two completely different fluids. It's really a study in contrasts. Think of the aqueous humor as the eye's active, free-flowing, water-like fluid. It sits right up front and is constantly being formed and reabsorbed in this really dynamic loop. On the flip side, you've got the vitreous humor. This is essentially a gelatinous mass tucked all the way behind the lens. It's built out of a fibrillar network of elongated proteoglycans, which basically means it's thick and fluid and dissolved substances diffuse through it very, very slowly. So active flowing water in the front and a stable structural jelly holding things together in the back.
Moving on to Section 2, anterior and posterior chambers, mapping the aqueous humor.
Now, even though it's all up front, this free-flowing aqueous humor is strictly compartmentalized around the iris. The anterior chamber, which is located right behind the cornea but in front of the iris, holds the bulk of this fluid. But when we say bulk, we are literally only talking about 0.25 milliliters. Meanwhile, the posterior chamber, which is that tiny space tucked between the iris and the lens, holds just 0.06 milliliters. Seriously, think about how small those volumes are. It really goes to show just how tightly constrained and precisely calibrated this active fluid system has to be.
Section 3. Aqueous humor key data. High-yield physiological facts.
Okay, let's look at some vital metrics because these are highly testable and they really highlight how specialized this fluid is. First off, the formation rate is a steady 2 to 3 microliters per minute. Its refractive index is perfectly dialed in at 1.1336, which is absolutely crucial for bending incoming light correctly. But here's the really wild part, the protein content. It's only 5 to 16 milligrams per deciliter. Compare that to normal blood plasma, which sits at a massive 6 to 7 grams. So why the huge difference? Well, even though aqueous humor comes from plasma, the blood-brain barrier aggressively filters out those large proteins. It has to, right? Otherwise, the fluid wouldn't be crystal clear, and we literally wouldn't be able to see a thing.
And where exactly does this superfiltered fluid come from? You can think of the ciliary body as a constantly running faucet. It uses a rich capillary network to filter plasma through diffusion, ultrafiltration, and active transport secretion. Because of this highly specialized active process, the final fluid ends up with surprisingly high concentrations of ascorbate, pyruvate, and lactate compared to standard plasma. This unique chemical cocktail is a literal lifeline. It provides essential nourishment to the clear structures of the eye like the lens and cornea since they don't have their own blood vessels to rely on.
Section 4. The drainage pathways, the outflow mechanics.
All right, so we understand the faucet. Now let's look at the drain. How does this fluid actually get out? Well, the eye relies heavily on the trabecular meshwork. This route handles a whopping 90% of all fluid drainage. We call this the conventional outflow. The leftover 10% kind of sneaks out via the unconventional or uveoscleral outflow, moving right through the ciliary body and directly into the suprachoroidal space.
Let's trace the exact, step-by-step path of that primary conventional outflow, since it handles the lion's share of the work. First, the fluid flows directly into the trabecular meshwork, which is essentially an open, spongy tissue. From there, step 2, it empties into Schlem's canal. Step 3, the fluid funnels out into a series of collector channels. And finally, step 4, it gets safely deposited into the episcleral veins, blending right back into the body's general blood circulation.
Which brings us to Section 5, IOP and glaucoma risk, when the balance fails.
Before we talk about the pathology, we got to establish our baseline. What is intraocular pressure, or IOP? By definition, it's the pressure exerted by the intraocular fluid on the coats of the eyeball. Normally, thanks to the dynamic equilibrium we just mapped out, where formation flawlessly matches outflow, your eye maintains a pressure somewhere between 12 to 20 millimeters of mercury, hovering right around a mean of 16. It's a perfect, delicate balance.
But what happens when that outflow drain gets blocked or compromised?
Obviously, the pressure builds, and this is a massive deal clinically. In 40 to 50% of glaucoma cases, we see raised intraocular pressure. This really highlights just how incredibly dangerous impaired drainage can be. This elevated pressure literally pushes outward against the inside of the eye, directly threatening the optic nerve, and ultimately a person's vision.
Now, it's not just a simple physical blockage. There are actually several external and internal factors that can throw this pressure off. Let's walk through them. First, age. Just like a lot of things, your eye's drainage efficiency naturally reduces after 40. Then there's blood pressure. Glaucoma prevalence is actually marginally higher in hypertensive patients. We also see diurnal variation. Get this, your eye pressure is literally higher in the morning and lower in the evening, completely mirroring your body's daily plasma cortisol rhythm. And finally, osmotic pressure. If a patient is given an intravenous drug like mannitol, it spikes their plasma osmolarity. This acts like a sponge, rapidly drawing fluid out of the eye and causing the intraocular pressure to plummet.
It is absolutely critical to note here that while a healthy, normal eye handles these daily changes and fluctuations smoothly, glaucomatous eyes suffer from dramatic, unstable pressure spikes. A healthy eye basically adjusts its plumbing on the fly to keep fluctuations minor, but a diseased eye, it just can't adapt, which leads to those really dangerous, vision-threatening pressure swings.
So I'll leave you with this provocative thought. Considering the incredibly detailed plumbing of the eye we've just mapped out together, how might modern clinical treatments specifically target these pathways to relieve pressure and save a patient's vision? I mean, could we medically widen Schlemm's canal? Or maybe somehow slow down the ciliary body's faucet? Deeply understanding this physiology is the absolute key to preserving sight. Thanks for diving into this with me today, and I'll catch you on the next explainer.